My goal for this talk is, I don't know how unusual it is because I haven't seen too many of the other ones. My goal for this one is that I want feedback on this one. And when I say feedback, I mean this one is going to be a mathematician asking for some engineering feedback on possible applications. I am absolutely sure as long as you're not throwing something at me. When I say feedback, yeah. So basically the background of this represents some of the work that I've done and that I did in my PhD dissertation, and some of it stuff that was following. The motivations were applied, but when you've got a couple of mathematicians working on it, we kind of like, well, what happens if you do this? And when we say what happens if you do this, it's mathematically motivated as opposed to engineering motivated. So now that there have been some theorems proven and other fun models created, I actually want to know what kind of possible applications can be seen. So my goal is to give a little bit of an overview of some of these things and just see if it wakes anything up in your head that it reminds you of. So my title is a little bit of a snarky play on the everything as a service. So this one's math as a service. And the title I kept fairly formal because I guess you're supposed to do that. But in a nutshell, we're going to be talking about reliability theory. And when I say dynamic and stochastic, what I mean is that things change over time and they change randomly over time. We'll talk about what those things are. All right, so for those of you that have not listened to me yet, I'm a mathematician currently at Dell EMC. So when I say mathematician, I do mean like pure mathematician. My research interests are generally probability theory, queuing theory, reliability, and stochastic analysis, some stuff in statistics and time series. I had to at least do something different with my hobbies. And if you've already seen my talk, then I'll throw one extra in. I like growing cacti, and I clean them off with canned air when they get dirty. So we would go, what are you going to do, brush them off? So, okay. All right, so there's a background. All right, for one, why should you care? Why are you sitting here with a potential of, presumably being thrown a whole bunch of scary Greek letters? All right, server downtime is costly and it makes people angry. Any kind of downtime is costly and makes people angry. And the other thing is that your traffic is never going to be steady. You see spikes, you see random fluctuations. There's no such thing as a steady flow in really anywhere, even fluid dynamics or what have you. And your workload's never constant. Two people hitting a database with two different queries aren't going to hit them with the same workload. That needs to be taken into account. So that's why you should care. Now, what are our goals here? We're going to walk through an overview of some mathematical solutions for server reliability. And I say overview, meaning I promise I will spare you the proofs that I forced on my dissertation committee. And I realized after I submitted these that leaving the cloud might be loaded terms with you guys. So I don't literally, I should have chosen a different metaphor. What we really want to do is leave the abstract realm and discuss how it might be useful to you. So that's the goal. So first we'll walk through an overview. All right, so I'm going to give you a mathematician's view of a server. It's a box. And lambda represents the arrival rate of jobs. So jobs come in randomly. Generally, they're modeled via what's called a Poisson process. And the specifics aren't really that important except that they're random. So, but the randomness does have an overall, we call it a steady state rate. An average rate, and that average rate is called lambda, so that's why you see that the dots are at least somewhat randomly spread out, so that I am emphasizing this is not a steady state thing. The server is just a box, and that G of W there is the service life distribution. So how long does it take to process a job through the server? How long does it take for you to actually get through the checkout line at the cash register? Right? How long does it actually take to scan all your crap and put it in bags? Every one of those is random, but there is a probability distribution associated with that. And then after it's completed, out come your happy completed jobs. And LaTeX wouldn't let me put a nice picture of Bob Ross up there, which I really wanted to do. I wanted to do little Bob Ross heads for the jobs, and they come out, but yeah, LaTeX wasn't cooperating. All right, so that's the mathematician's view of a server. So just a couple of brief overviews on talking about reliability. So the lifetime of anything, your own life, or a server, or a car, or a component, or any other object, is essentially a random variable until you actually die. So we're going to let y represent that random variable. There's lots of different ways to represent the probabilistic distribution of that. In basic probability, you may have seen a PDF, you may have seen a CDF. We're going to look at a perspective called a survival function, which is actually the complement of the cumulative distribution function. That is the probability that my lifetime exceeds a particular time t. So what is the probability you survive past 50 years or whatever? The other one of interest, in particular in engineering, is going to be your hazard function, which is derived, and I skipped the derivation because I promised I'd be nice, but it's the instantaneous rate of failure. So you can look at over, that's the mathematician's version, but in general, over some block of time, how many failures do you experience per block of time? Obviously, when you take the limit as that block of time goes to 0, you get an instantaneous rate of failure, just like you take a slope and then end up with a derivative or a tangent line. That's all that is. In effect, it's actually the PDF divided by the survival function, and that can be derived. But that is one measure of reliability, and it can be derived. It's just a different way of expressing the same random variables distribution. Survival function, hazard function, CDF, it doesn't really matter. We're actually going to focus on the survival function because it's pretty interpretable and it's pretty easy to understand. But I threw the hazard function in there in case anyone in here was actually into reliability, because that's more standard in that field. Okay, so let's now take a look at something real quick. So here, the reason I talked about a hazard function is this is going to be essentially some people call it a breakdown rate process, some people call it a hazard rate process. We're going to look at R naught of t. That is going to be the failure rate function, assuming that your server is idle. No jobs are going through it, you just power it on and it's sitting there. I assumed constant because it was a lot easier to draw the picture, but it may not necessarily be constant. Now what's going to happen once we start adding workload, so at that capital T1, the first job comes in and makes a request. And that request is going to create some kind of stress on that server, that random variable h1. So that means from our baseline hazard rate, we have now increased our failure rate by that random h until that job is completed. It's stressing out the server. And then once the job's completed, yay, the stress is now gone. That's random. So that B is basically the random failure rate because, again, these jobs are coming in randomly, according to a distribution, but still randomly. And the stresses are random. Now here, you have the second one coming in. It brings more stress than the first one did. And now a third one comes in before the second one finishes. So note that basically you have to add those two stresses because you haven't finished the second job. Once you finish the second job, its contribution to the stress of the server, if you will, is going to drop down, but the third one is still there because, as you notice, there's no T2 plus W3. Those W's are going to be the time it takes to process that job. So basically, T plus W for any particular job, that's the total time that it's going to be spent. That's the time it's spent in the servers. How long did it take to actually complete it? So T plus W, so that W would be the length of time it took to complete it, and there's the time of completion. Now what we can then do is to say, how do we express that failure rate, that random failure rate? Well, it's a baseline failure rate, assuming it's idle. And then all we have to do at a particular point in time is look to see which jobs are still going. That's what that one is. That's an indicator function. Is it true? Is that job still running at that time? So mathematically expresses an indicator function. Multiply it by the stress because it's either 0 or 1, right? It's just a binary function, on or off, yes or no. If it's on, then it contributes stress. If the job is not running at that time or hasn't come in at that time, then no contribution. So quick example here, like if we took T here, then the first job would have no contribution. The second and third would. So you would simply have R naught of T plus H2 plus H3. If I were back here, then 2 and 3 haven't come in yet, but if I were in here, then B of T, if T is between basically T1 and T1 plus W1, then it would be R naught of T plus that H1. So just to give a quick example. That's the random process that's going to describe it. This was actually done in a 2011 paper. The randomness part I added. They assumed the stress was constant. Now I assume the stress is random. I don't know the distribution. I don't know anything about it. I don't even know if it's continuous or discrete. I don't know anything. But what can you do with it? Whoa, all right. Yes, I am assuming the workload impacts the failure rate. And that would be a good question. Like any of those kinds of things, definitely write them down. Then when I ask for feedback, like that kind of stuff is the kind of stuff that I want feedback on, as what kind of workload, is that really true, all that kind of stuff. So when I did this, when I said server, mathematically, I mean the queuing theory version of a server. So that can mean something in engineering, it can mean something in business, it can mean literally. So for your application, maybe it does and maybe it doesn't. Those are the kinds of things I do want to know. Somebody else had a question. I mentioned that it was constant simply to make it easy to draw. It doesn't have to be constant. That's so we can see clearly the contributions of the random stresses.
Are you also assuming that after your stress goes away, you return back to the baseline?
After the stress goes away, you return back to whatever, you basically take away the contribution that that job brought. So if, for instance, in time 1, yes, we do return to the baseline rate because there's nothing else adding stress. I assume there's no lingering stress, if that's kind of what you mean. Okay, no, we don't assume that. No, we assume that when it's out, it does not leave any lingering effects on the system.
And if you did assume that, over time you would basically accumulate some idea of where on the system.
I like that, save that. Like these are the kinds of, that's the kind of stuff that I do want to. Yeah, so that's kind of partly my goal is to, 1, find applications, and 2, find other generalizations. So suggestions like that, because again, mostly mathematicians.
To add to that, clearly you do have lingering stress on systems such as caches.
Right, so yeah, that's a good thing to consider, because I'm trying to continue this kind of research, so building that out would be good to consider things like that and how I would incorporate that mathematically. Okay. So this is basically, we're going to take the graph and then some other assumptions that I made. The arrival times are random. Even the arrival rate can depend on time. So you generalize that to something called a non-homogeneous Poisson process. So that arrival rate isn't necessarily constant. The service times are random, and any service time distribution you want. And those stresses or workloads are also random. Any distribution you want, continuous or discrete. The equation that you then see is the closed form of the survival function with, to my knowledge, the most general conditions that you can create, except for, I guess, now considering things like accumulating. Oh, stop it. You don't want to see the paper I'm reading right now. Okay. That's the closed form solution. Now, the equation itself is not particularly enlightening. It doesn't give you any kind of major insight into what's happening because it's so general, right? These are just general distributions, this being the integral of your non-homogeneous arrival rate. And then that E is simply an expectation operator over the random stress. The point here is that it's a closed form solution. It can be calculated, and it can be calculated exactly. I mean, good luck, I've tried actually. You'll probably need some numerical, when I say exactly, I mean mathematician says closed form, and the engineer will say, you're gonna have to use some numerical approximations to those integrals. I've tried, I promise. However, a lot of reliability models do kind of expect you to have to use a little bit of black box algorithm, a little bit of learning, whatever. There's an analytic solution to that, and it's one that's extremely general. But we can generalize it more. We can change it up a little bit. Now, I don't know if clustered task server is actually a real thing in engineering. We just kind of named it that as mathematicians. If that's actually a term, don't assume that I literally mean the term that you know, so I'll explain what I mean. We'll keep that same arrival rate, but now we're going to assume that this server is partitioned, and each one of those channels accomplishes a certain task or piece of a large task. And each one of those channels has a different service distribution. So when a customer comes in, he will select anywhere between 0 and all, I guess 0 because we have to consider it mathematically, but practically, between 1 and 4, or 1 to n. And he will select some number of these randomly and say that I want to put them in order for multiple things. And maybe those multiple things, say the first customer comes in and he wants whatever channels 1 and 3 can do. Now, customer 1 is not considered served until the last one of 1 and 3 is completed, right? His job's not done until he's gotten his entire order, not just the fries. Okay. The second one comes in. He wants, say, 3 of them. Now, it's totally fine for one of those queues to kind of back up they operate in this model, they operate without knowledge of the other. As far as we don't consider, like this isn't considering load balancing, that's something else which I have considered. That one doesn't have a closed form. It almost does, but not quite. It's not load balancing. It literally just, it's by what, they accomplish different tasks. So we're not gonna split loads. It's another thing to consider, but the math gets ugly and I wasted about 6 months of my life trying to figure it out. So, and I wanted to graduate. So I put that aside for now. And there's a couple of things we can consider with this when we change it up. We have options. One is when the customer comes in and wants to select different tasks, he can select, say, he'll select the first one, yes or no, second one, yes or no, third one, yes or no. That's a Bernoulli random variable if I don't know what he's going to select in advance, flipping a coin. It can be independent, as in, you know, the probability of him selecting the third one has nothing to do with whether or not he selected the first one. Or it may not. Maybe it does depend on it. This dependent channel selection is new. This one will actually give you simply a binomial distribution for the number of channels that were selected. This one gives you a generalized binomial distribution, and that distribution is actually new as of 2013. My advisor did that one. The other ones, the other distributions that followed are mine. And then you can even vary that dependence, and I'll actually go into it a little bit. I can have a constant dependence. I can have a temporal dependence, that is, it depends on time. So the dependence itself is dependent on time, and totally random dependence. So let's go into that a little bit with that independent channel selection. We're going to assume that all of the channel selection probabilities are equal. Why? Because I like binomial distributions, and I don't want to have to enumerate everything. You can still do it. It's fine, but my formula is prettier if you just assume that. All right. So if each of those channels then has different service time distributions, then the overall customer service distribution is actually going to be the max, so the argmax over that, all those. Like I said, I'm not going to make you do all of that stuff, but that's what that is. Now, the stress to the server, this is where I had to make some simplistic assumptions and working on a generalization. So n is the random number of channels that were selected by that customer. I assume that each one of those basically is a constant stress times the number of channels selected. That's a little bit different from the random stress I assumed prior, but then you have multiplications of random variables, and then your math, like I said, it gets kind of ugly because I don't like convolutions. So we keep it kind of simple just to start and see what happens. That means simply that this is now a random variable with a very nice binomial distribution, and that formula I showed you earlier is actually, that's that same formula, it's just for a specific case. So what we thought was a totally different model actually was simply a special case of the previous model I had generalized earlier. Like I said, the formula is not particularly enlightening, but it's there and it's closed form. Now we get to have some real fun. This is the real fun, okay. All right, dependent channel selection. Now, this is a particular kind of dependence, and it's called first kind dependency. Whether or not the first channel was selected will affect the probabilities of the other ones being selected. So let's say a customer comes in and selects the task that the first channel does. Then that means I'm going to weight the other ones in favor of being selected, as in either, like if he's going to select one, then he's probably going to be a heavier workload. Doesn't mean he will be, but I'm going to change the conditional probabilities of the next one. So the next probabilities are affected. It's called first kind dependency. There are other types. I've published papers on them. Since you could do an entire lecture on these, I just decided to stick with this one. And what you're going to do is you're going to introduce what's called a dependency coefficient between 0 and 1. And that is how you actually change the probabilities and weight them in a new way and still keep the mathematical properties that you actually want, which is in our case identically distributed but no longer independent. That allows us to actually still do most of the math that we wanted to. In sense, giving the survival function in closed form still, even though the channel selection is not independent anymore, which actually is going to model a more realistic assumption. You know, a lot of times you're not going to, nothing operates in a vacuum. I can still give you the survival function in closed form. I didn't write this one because it's a similar, again, it's not particularly enlightening, but you can still give it. So we've got some actual pictures here. Now, if you relax even that dependency coefficient, as in I can make it, that should be sine of t. Dang it. Oh, I hate typos like that. All right. I blame Mathematica, it's its fault. So this is the survival function for a dependent channel selection when that dependency actually varies with time. And you can actually see that sinusoidal dependency reflected in what was a monotonic survival function. So the monotonicity isn't actually always the case. So that's one example. Now we can have a lot more fun and make it random. So these are basically the particular parameters that I put in. One is a 2-channel server and one is a 5-channel server. And what I did is created a 3-state Markov chain, not absorbing, for those that attended the last talk, regular one, as in you can move among all 3 states just fine, with this particular transition matrix. And these are the possible states. So the dependency goes from close to independent, halfway between independent and completely dependent, and almost completely dependent. Now I'll note here that when we say completely dependent, let's imagine flipping coins. If you're completely dependent and first kind completely dependent, if I flip the first coin and it becomes a heads, all the other ones are going to be heads. That's completely dependent. And if it's completely independent, if I flip that first coin, it has no bearing on what the other coins turn out to be. And so that means that anything else is going to be somewhere in the middle. So delta equals 0, total independence. Delta equals 1, complete dependence. Everything else is a little bit in the middle. So what happens if you kind of vary this a little bit? Now you can see how much the survival function is affected when you move from almost independent, somewhat independent, and almost completely dependent for a couple of different channels. All of those little jumps that you see are the effects of that dependency changing as that random process is realized. So you can model that as well. Why do you care? Why are you? Oh, sure. So what's happening here is that every time this transition happens, so every time it moves, say, from one state to another, one of those jumps the jump is going to represent essentially a new dependence for that amount of time. I left off the continuous Markov dependence, but that's okay. We'll just stick with discrete. Why do you care? Why are you still sitting here? Okay, isn't assuming independence enough? Aren't you just making things completely complicated and, you know, why? This is just satisfying some mathematical itch you have. Not exactly. So then the natural thing to do is, why does it matter? What if you assume independence when it actually is dependent? So here, these are a couple of different things. Now these etas, this is the constant stress multiplier that's going to go with the number of channels. So how big a stress does each task create? So small, not so small. What this is going to tell you is this is the percent difference if you assume an independent and dependent channel survival functions in the long run. Now what this means is that over time, in particular for larger stress, that difference, even for small numbers of channels, 10, up to say 300, you're looking at close to 1,200% different. In other words, you are way off. If you assume independence and it's not true, you are way off. The only time you can really just, let's just take the simple assumption and just not model the dependent crap, is only when you have small channels, small stress per job. Other than that, you're going to be way off. Okay, now what? All right, so my goal here, and I realize this was a high-level overview of something that I could have held you captive for a couple hours for, but the goal was just to at least see what these kinds of models or these kinds of diagrams inspired as far as your thought process goes. The goal is to either A, do something with them, B, look at things, notice things that I hadn't considered because I'm a mathematician, and I didn't notice that there are some other considerations that work in reality that you didn't see reflected there. And then what kind of applications? So I made a couple of questions. So one, how would you define stress to a server? And you can, I'll basically read these and then just kind of take feedback. What metric do you use to measure traffic? Do you collect this data? And are you actually interested in the notion of network reliability? Meaning, we've only talked about a single server thus far. When I told you I could give you the closed form of that one server, what happens if you build a network of them? And when I say reliability network, I mean, a reliability topology. So For instance, think Christmas lights. If they're in series, if one dies, the whole system dies. If they're in parallel, if one dies, no big deal, you still have another one working. So that's what I mean when I say network topology of reliability. I can still give you the closed form for any reliability topology that you want, even under these general conditions. No matter what topology you give me, if you build a server with basically a network of servers like this, any one you want, I can still tell you the closed form of that survival function. It's not nice, I'm sorry, but it's still there. So that is, are you interested in that notion? Because I considered putting it in the talk and then decided I'd actually ask and see if you wanted to know, and that's where I'd hope for a whiteboard, but it's okay. So I feel like I either A, overwhelmed you, and you're still here, so that's one thing. So that's probably not too bad. But at this point, I kind of want to at least open the discussion so I can go back over stuff. I can answer other questions. If you see other things or have comments to point out, then I'll take those. Yes?
I have a question for your last bullet.
Last bullet.
Yes, about the notion of network reliability. So you're starting off with a broad definition of server.
Yes.
And now you're talking about effectively networking the servers. However, your the scope of your equations and the scope of your focus, are you talking about from the server side or from the inside of the network, or both?
Can you clarify that a little bit to make sure I understand?
Because in a storage network, I've got queues and I've got buffers on both sides of the link.
Okay.
And the thing is that, especially in certain types of storage networks, which can be non-deterministic, you wind up with very inconsistent data paths on both the server side and inside the network. So some networks have the basic chipsets inside of a switch have arbitration queues. And in certain types of storage networks like NVMe or fabrics, you've got queue pairs on the endpoints. So you have the possibility of a stacked network reliability problem from your perspective.
Oh, I see.
And ultimately, even if I can model this inside of math, I guess I'm still a little curious as to what I could do with this work to alleviate some of those pressures.
I got the sense that this wasn't network in the sense of the SAN, the physical.
No.
But an aggregation of the concept of the server. So that it's like social networking isn't analogous really to Ethernet. This is closer to a social network.
So when I say a reliability network, if you think about something like, say, your two lungs don't, well, okay, they actually do kind of look like they're in parallel. Because the thing is, like, if they're parallel cities, they actually look like it. There are certain components that you can draw that operate essentially in, say, parallel, but they don't literally sit next to each other, or they're not even wired next to each other. It's just the system, the way the system works is that as long as one of them is operating, then the system is still good, or some collection of those. Yes. Okay, so that's what you guys called it. I wanted to avoid that word because I have it loaded over here. But I guess in your term, you would call those dependencies?
Well, in the way you just described it, yeah.
Okay.
If I have the overall goal of a process or some procedure running, and there is any dependency of any of those operators where one goes
Okay.
down or one slows down, the overall execution time is varied, then those dependencies.
Okay. In engineering, they would, or at least since I come from a manufacturing engineering background from a master's, they call those basically block diagrams or block topologies. And then so if you guys call them dependencies, I try to make sure I learn those. But yes, that's essentially what I'm trying to model is the reliability, you have to stick with essentially the reliability network and how the server operates with those various components. So for instance, an airplane operates with wings and landing gear and all these other things. If you lose a wing, it's okay. If you lose a wheel, I mean, it's sort of okay. You can still land a plane sort of with one wing. You can lose an engine, right? Okay. Sorry, nobody's flying out, right? Like,
That's not a bad way to look at it, because in a really large environment, you will have ratios to say, only if I lose this much equipment in a certain area is it worth going on to fix it, right? So you may have a stack of like 40 devices. If you lose 2, you don't care. You lose 20, now you do, right? And so, that notion's not, you're welcome.
so yeah, the clarification on that is the network reliability is probably a little bit different than what you would consider your standard, literal computer network. It's the reliability network, or dependencies as you would call them. And then what you can do then is each one of those components itself is going to have a survival function based on traffic coming to it. And then depending on how these interact as in, overall, if your entire system is running, I can still tell you what the overall survival function of that entire system is if you can map those dependencies out for me.
Please put this to specific big conference.
Okay.
This is beautiful material for that conference. I cannot even.
Sure.
In the HPC world, this is magic.
Yeah. If you give me information, then I'll submit it. Cool.
And they love me.
Yeah, they don't mind if the paper has been published previously because it's a PhD thesis. Well, parts of it are PhD thesis, parts of it are papers published afterwards. Okay. Cool. Yes.
I think there's two things I'm trying to get my head around.
Sure.
The first thing is that systems really aren't random in any form, our systems. But they're complex, and there are causal dependencies that are complex, but really not random. And that leads me to the thought also about how do you model things like cascading failures, which are a common thing that we have at scale.
So,
something goes wrong and then causes other things to go wrong.
can you clarify what you mean when you say that your systems aren't random? Like you're saying, because
Well, for instance, scheduling.
Okay.
It isn't random.
Right.
It's either round robin or something like that. I mean, yes, there are some supercomputers, HPC, that use sort of atomic spin to get some random number to feed into some security, some compression algorithm, some encryption algorithm. But generally, computer systems aren't random. And so, absolutely, I agree with that. So I'm just trying to, where do you cross over? Where does the random model actually work?
I'll give you the kind of background to the original paper that I started generalizing this work from. They looked at what they called a web server, and they looked at traffic to a web server, as in like hitting Amazon or whatever, from kind of that perspective. Does that help, or?
So something like that, you could see, yes, well, again, it's not actually random, but it is pseudo-random. It's as close as
Okay.
But in the back end of a system, let's say a network, a cluster, it's much less random because you're doing things like scheduling, you're doing things
Right.
like reacting to protocols, etc.
So then the next thing that I tried to consider was things like what happens when you do start interfering with what could be if you just didn't interfere random traffic. That's where I did try to look at what happens when you do have, say, load balancing. As far as the mathematics was concerned, and I if you feel like diving into these, what ended up happening is that it was a complete memory process, whereas a Markov process is memoryless. This one completely dependent. I could not get a closed form, only a conditional form. So when you start interfering with things, and there are aspects of queuing theory that deal with it, I didn't go down that road and didn't want to until I found that there was interest in it. So I think it seems like from your perspective, at least from that back end, these types of things do assume a lot more randomness in traffic than you would actually see, in which case probably the math, it was designed to be as broadly applicable as possible to things like, even road traffic, I guess, is somewhat not random because we control it with stoplights and things like that. But you're right, there's some element of randomness. What I would hope then is actually to potentially change where I'm taking that dependency coefficient and maybe moving it somewhere else to account for that, and then you can shift it towards closer to deterministic as a generalization, hopefully. But no, that's an interesting.
It's very